So what is nuclear magnetic resonance, or NMR? This is a technique that we use to explore the structure of molecules by detecting their nuclei using a signal that is of the radio electromagnetic frequency. We kind of see kind of a rough explanation here that certain nuclei, particularly ones with an odd number of protons and or number of neutrons, they are sensitive to this technique and will absorb radio frequency electromagnetic radiation. And that's because, or what it's based on is their nuclear spin, very similar to the electron spin that you learned in general chemistry. So these nuclei are spinning, and then because they are charged, they generate a magnetic field. And it's that field that is going to be what this electromagnetic radiation will be interacting with. So particular nuclei that will be of interest in organic chemistry, especially in sophomore, is the regular hydrogen nucleus, so the nucleus we most commonly think of when we think of hydrogen, as well as the specific isotope of carbon known as carbon-13. So once again, the nuclei have spins, and these spins generate a magnetic field internal to the nucleus that acts like a little mini magnet. And if you've ever seen demonstrations of magnetic bars and magnetism, you know that it can be manipulated, those fields. And that is what that radio frequency radiation is doing, is manipulating them. Now, in order for this technique to be sensitive, though, we need it to be able to detect differences in these nuclei. And the only way that the nuclei can be sensed as having anything different is if you create some kind of, you have to break the fact that if the poles are pointing in random directions, it's sort of, we have no reference point if you don't have an external magnetic field. And so really the only way that we can make to make NMR work is we have to apply an external magnetic field. Now, if you think about it, our Earth has a magnetic field. That's how our compasses work. So what that hopefully makes you realize is if that's not good enough, it must mean that you need a stronger one, and we do. In fact, we have to use such a strong magnet that it's actually generated in a very special way using a supermagnet. Now, we'll come back to that later when we take a tour of our nuclear magnetic resonance lab. Now, just to kind of zoom in again on this concept here, once you apply this external magnetic field, now the system, particularly the electromagnetic radiation going into the system, can tell whether a nucleus is aligned with the external magnetic field or opposing it. And if you think about magnets, if it's aligned with it, then it's going to be lower energy because it's where the field would like it to be. When it's opposing the magnetic field, then it's actually at a much higher energy state. So what we've done is we've split the energy state of these nuclei, or at least we've generated two different energy states that they could be in. And what happens is when they absorb the electromagnetic radiation of this radio frequency, they absorb them at a certain frequency where it is enough energy to take the spin, which we call alpha spin state, that's aligned with the magnetic field, and flip it into the energy state where it's opposing it. And it's very sensitive to the exact difference in the energy. I want to emphasize, because we're back in that quantum realm where there's only two energy states, where it's either aligned or it's opposed. And that's what's going to be very important, because that's going to make certain nuclei whose environment makes their energy split a very specific split. As you can see, it's sensitive to how strong of a magnetic field it feels. And we'll see how that comes into play later when we talk about chemical shift. And so that's the key to it, is that it depends on how much energy split there is between the opposed and aligned. That determines what frequency of radio wave is absorbed, or more specifically emitted, but we'll get that in a moment. And we have this slide a little earlier, and it's just mentioning, it's kind of what I was talking about there. If nuclei are in different environments, typically what that will mean is the electron density is different. And electrons, if you think about it, they are sensitive to magnetic fields. In fact, they will generate an opposing magnetic field and start cycling around. when they feel that external magnetic field. And then the field that they generate, the electrons, opposes that external magnetic field. That's going to actually decrease the strength that the nucleus feels of the external magnetic field. And that's why that's called shielding. And we'll get into shielding more when we talk about chemical shift. So once again, this is just showing that idea. Different nuclei with different, also even like, we'll talk about shielding more with chemical shift, but this is even saying if you have a different strength magnet, you're going to cause an initial difference, you're going to cause a different splitting in the energy just straight up, with regardless of the chemical environment that the nuclei are in. And what happens is the strength of the magnets actually gets associated with a center point frequency of radiomagnetic radiation that is common for that NMR machine. And so even though it's a different magnet strength that's really separating these machines, we oftentimes label them based on this radio frequency associated with that strength of magnet and the split that it would cause. So you'll actually not see Tesla in the name of the NMR machines, but rather megahertz, 60 megahertz machine, 300 megahertz. And so here's the NMR, kind of a pulsed Fourier transform NMR. And here, this little Lego diagram, which I someday hope to finally have built for me and I can own, of an NMR. It's got the probe, it's got a little drawing of a computer that's connected that controls everything, as well as the giant cylinder that contains all the probe, the active probe, and the cryogenic liquids that keep the magnet cool so that it can function properly. I'm going to let Caleb now. We're going to walk over to our lab and tour it with me as Caleb describes our own machine and gives us a little bit more details about the parts of the NMR.
Hello, I'm Caleb. I am the instrument technician here for the chemistry department at the University of Laverne. And one of the main instruments I've been working with is the NMR, which stands for Nuclear Magnetic Resonance. So what is NMR? Well, let's break down the name. So in this case, nuclear doesn't mean like bombs and things. Instead, it means the nucleus. We're using magnets, hence magnetic, to look at the nuclei of different molecules and detecting them. But before we get too deep into how we look at the nuclei, let's talk about the instrument a little bit. So you definitely can see this. It's this very large bulbous instrument. And the reason for that is because of the properties of the magnet. So within here, near the center, there's a magnet that's superconducting. What that means is the magnet doesn't lose any energy to resistance. It is such an efficient magnet that it doesn't lose energy as heat. But to get it to that point of being superconducting, we have to have it really, really cold. So within these big dewars, we have a few different layers. On the very inside, where the magnet is, we have liquid helium. Liquid helium is right around 4 degrees Kelvin, so very, very cold, very near absolute zero. And that's what the magnet is immersed in. So there's a shell filled with liquid helium. Outside of that, we have a shell that has vacuum, and that helps insulate it, so the helium will slowly boil off and it will slowly evaporate. And so to have that happen as slowly as possible, so we don't have to refill the instrument, we have that vacuum. And then we have the outer layer, which has liquid nitrogen. Liquid nitrogen is around 200 degrees Kelvin, or minus 80 degrees Celsius. So it's not quite as cold, but what it serves is it's a buffer so that the liquid helium doesn't boil off as fast. As I said, we have to refill it fairly regularly, and the fact that we have the liquid nitrogen layer and then the helium means the helium, which costs thousands of dollars per fill, we only have to do every 4 to 6 months, whereas the liquid nitrogen, which costs tens to hundreds of dollars per fill, we do every few weeks. So having the extra layer of liquid nitrogen means that we don't have to spend quite as much money refilling with helium. Then, so that kind of covers what we mean by the magnet. Let's move back to the resonance and the nuclear part. So I said that we look at the nucleus of molecules. And how we do that is we use this magnet and we tune it to a frequency. And that frequency is a resonance frequency for different atoms. This instrument, you can see it has a nice 400 on the side. It's a 400 megahertz instrument. That means once we tune this magnet to the frequency of hydrogen, it resonates at 400 megahertz, and we're able to pick that up. And so that we tune it to that frequency, and then we can look at all of the hydrogens within a sample in our instrument. So what does a sample look like? Well, right here, we have a little tube. So there are a couple parts. We have this little spinner guy. We use pneumatic air to put a sample in and out, and so this helps the air catch the sample. Also, you can see the black and white pattern around it. That's for if we're spinning a sample, it can tell how fast it's spinning based on a little laser checking that. And then we have the sample here filled with liquid. So most of this is solvent, and there's just a little bit of your liquid dissolved in it. In terms of how much sample you need, you only need a few milligrams to get a good NMR signal. So yeah, it's a very sensitive technique in that sense. But as I said, we use the magnet and it looks at all of the hydrogens within your solvent or within your sample. So then how do we differentiate between the solvent and our sample? And to combat that, we have to go back to resonance. So have you seen or heard the term deuterated or deuterium in terms of a solvent yet in organic? What we use here, we use a deuterated solvent. And so what that means is we use a different isotope of hydrogen. So if you remember, an isotope has a different number of neutrons for the element. So hydrogen normally is 1 proton and 1 electron. Deuterium, which is an isotope of hydrogen, has a proton and electron, but it also has a neutron in the nucleus. And the fact that there's a neutron there means it will have a different resonant frequency than hydrogen. So when we put it in the instrument, it appears at a different frequency. So all of the solvent, if we replace all of the hydrogens with deuterium, will essentially be invisible for what we're looking at in terms of hydrogen. Another interesting thing then with the NMR is you have a probe, which is what you use to look at the different elements. So I have one over here that isn't currently in, and I'll pull it out. So this is a probe, and there's currently one in the instrument that is in the center, and it has this little spot in the top, if you can see, and that's where the sample will rest. And then it has 3 different nodes here, and that's what we're tuning to the different frequencies for different elements. So on this one, you can see we have one for hydrogen, so we can look at our sample. We have one for carbon, which is really useful for looking at organic samples. And we have one for deuterium. So how this probe is set up is we have the deuterium as kind of a stabilizing probe, because we have to take a bunch of measurements and then average them. That's used to, it's called the lock channel. And then we have these 2 that we can measure with, the hydrogen and the carbon. So we can do experiments that look at both. And that's a bit of an introduction to NMR. Once we get back on campus, feel free to stop by and ask me any other questions you have about NMR.